So in terms of talking about enthalpy changes and Hess's law, we're going to start using a number of literature values. So this is the first video that will go over certain enthalpy changes that are in the data booklet and that are very common for use with energy cycles and simultaneous equations with Hess's law. So before we do that, just to mention about what it means to do something. Wow, that was a bad little marker line. We're going to do that again. Under standard state conditions. So it's important to remember when chemical reactions take place, it involves not just breaking and forming chemical bonds like covalent and ionic bonds, but also intermolecular forces. And so the total enthalpy changes for reactions don't just depend on bonds breaking and forming. It also depends on the states and other conditions that those reactants and products are under. So enthalpy change literature values are usually recorded under the same conditions. That way, when they're reported, everyone knows that the conditions were consistent and that they can be used to compare to one another. So you could have conditions that are called standard state conditions, or STP. You could also have standard ambient conditions, and those are SATP. Both of these conditions are listed in Table 2 of the data booklet. Really, the only difference is the temperature. STP is 273, standard state is 298. And I think I made a mistake up here. It's not standard state, it's just standard conditions, or STP. Standard ambient conditions used to be called standard state conditions. So the little rhyme I had was STP is 273, standard state is 298. That's the only difference between the sets of conditions. Otherwise, the pressure is the standard pressure. When we talked about like redox and electrode potentials, concentration is 1 molar. And in this topic, it's going to be important when we talk about standard state conditions and we refer to elements, we're going to be referring to them in their most normal, stable form. So for example, oxygen's standard state form is O2, not another allotrope like O3. Usually when we talk about carbon, we're going to be referring to graphite rather than referring to carbon as diamond, since its normal form is more like graphite. Okay. If a value is a standard value, it has been recorded under these conditions. So we're going to learn 2 enthalpy changes in this video, and they're both referred to as standard blank enthalpy change. And so it means that it was recorded under those conditions. The symbol for that sort of looks like a circle with a line through it, and it's a superscript. So a standard enthalpy change will have a delta H and then this sort of symbol up to the top right. So the 2 standard enthalpy changes that we're going to learn about in this video are standard enthalpies of formation and standard enthalpies of combustion. You sort of need to know their definitions and how to represent them as equations. But they're 2 very common literature values that you'll get asked to use, and they work nicely together in energy cycles. So they're very common to come up in problems together. So standard enthalpy changes of formation, delta H with the little standard state symbol, plus a little subscript F, that tells you that it is a formation enthalpy change. It's the enthalpy change when 1 mole of a compound is formed from its elements in their standard states at 298 Kelvin and 100 kilopascals. So for example, for methane, if I skip down here, we would represent the enthalpy change of formation with this equation. Carbon and hydrogen, which are the elements that are in methane, they're in their normal states. So carbon, solid, like graphite, and H2, which is the normal form of hydrogen. You need 1 carbon and 2 hydrogens, and that forms 1 mole of methane in the gas phase. And that enthalpy change would be negative 74 kilojoules per mole. So this equation represents the equation for the standard enthalpy of formation of methane. Another example, the standard enthalpy change of formation of ethanol. Ethanol is C2H5OH. So in total, there are 2 carbons. So on the left, there should be 2 carbons in carbon's normal state. There need to be 6 hydrogen atoms, which comes from 3 H2 gas molecules. There needs to be 1 oxygen atom, so there's a half of an O2. And then you get the standard enthalpy change of formation for ethanol. A couple notes about the enthalpies of formation. Elements have formation values of 0 because there is 0 enthalpy change when you form an element from itself. So just based on how that term is defined, elements have values of 0. All these values are listed in Table 12 of the data booklet. The title of that table is Selected Compounds Thermodynamic Data. and we'll use it in this video. The other enthalpy change that I want to talk about is standard enthalpies of combustion. The little C here denotes that it's about combustion. We've already looked at these in a lab we did before. The enthalpy change when 1 mole of a substance is completely combusted in oxygen at 298 Kelvin and 100 kilopascals. These values are in Table 13, Enthalpies of Combustion. So looking at methane and ethanol again, the equations that go along with the standard enthalpies of combustion are when you take methane plus 2 oxygens, makes CO2 and makes water. And that has this large of an enthalpy change, very exothermic. The enthalpy change for the combustion of ethanol, it takes 3 oxygens, makes 2 CO2s, and makes 3 waters, and that's the enthalpy change. So just a quick note for clarification. Enthalpies of formation, the thing that has to be 1 mole is the product, because they refer to forming a compound. So you're forming a product. So you always have to have 1 as the coefficient for the product. So if you look back at the examples, when we formed methane, there was 1 mole of methane in the product, 1 mole of ethanol in the product, and it didn't matter what the coefficients were for the reactants. You could have 2 of something, 3 of something, half of something, whatever you need to do to make 1 mole of the product. For combustion, you always list 1 mole of the compound or element that's being combusted. So it's for a reactant. So again, looking back, when we talked enthalpies of combustion, there's always 1 mole of the methane, if this is its standard enthalpy of combustion, and there's 1 mole of ethanol, and then the other things in the equation can be more than 1 or can be fractions. This can be a little bit confusing to apply the right term when you're looking at products that are formed by combustion reactions. So for example, this equation right here, carbon plus oxygen makes carbon dioxide. This equation could be is listed in the data booklet under 2 different names. So one name is, I'm looking at the combustion enthalpy of carbon, right? One mole of carbon fully combusted makes carbon dioxide. So this is the enthalpy of combustion for carbon solid. But this is also something else. It shows me how CO2 forms from its elements. So this is the enthalpy of formation of carbon dioxide, right? And so it doesn't really matter. The enthalpy change value is the same. The same value is listed in the data booklet for the enthalpy change, but just note that sometimes 2 different terms apply, but you have to know that this is the combustion value for the reactant and it's the formation value for the product. Same thing goes with this equation here. Down below, this looks like the enthalpy change of combustion for hydrogen. And it is the enthalpy formation for water. Okay, in terms of the energy cycles with enthalpies of formation and combustion, the best way to look at it is that you're going to have elements turning into compounds, and then the elements and the compounds can both be combusted to turn into CO2 and water. So I don't think that was a very clear explanation of that. Essentially how it works out is that the change from the elements to the compounds is the enthalpy change of formation. That's usually represented by this arrow. And then these arrows for the elements to turn into CO2 and to turn into water, those are combustion enthalpies. And for the compound to turn into CO2 and water, that's also a combustion enthalpy. So you end up getting a cycle where you can take the elements and put them together into a compound, and then you can burn the compound, and you should get out the same amount of enthalpy, same enthalpy change overall when you combine these two, as if you just take the elements and you combust them and turn them into carbon dioxide and water. Okay? Same idea, when we look at the simultaneous equations, you can take elements, turn them into a compound. You can then take that compound and turn it into CO2 and water by combusting it, or you can cancel out that middle step and just turn the elements straight into carbon dioxide and water, and the overall enthalpy change should be the same. So let's try it with a sample IB question. Calculate the standard enthalpy of formation of ethanol using standard enthalpies of combustion. So the first thing you've got to do is come up with what's the equation for the standard enthalpy formation of ethanol? Well, we know what ethanol is. Ethanol is 2 carbons, so C2. It's got an OH, and so we could figure out that it's eventually going to be C2H5OH. All right, now we've got to come up with the rest of the equation. So I see there's 2 carbons. I see there's 6 hydrogens. And I see there's 1 oxygen, so that's a half O2. Let's bring that arrow back. So this equation is the enthalpy change of formation for ethanol. Okay, and then what are the equations and the literature enthalpy change values for the standard enthalpies of combustion? Because the question directed me and told me I should use standard enthalpies of combustion. So this is the combustion equation for ethanol. It's also the combustion equation for the elements carbon and the combustion equation for the element hydrogen. There is no combustion equation for oxygen because really oxygen is what causes the combustion, so you can't really combust oxygen anymore. It's already fully oxidized. So where do I find these values? So here's a snapshot of table 13. If I want to find enthalpies of combustion for hydrogen, then I look here and it says it's negative 286. And I want the one for carbon. So I have 2, right here it is, carbon graphite, negative 394, which is this one. And then I look for ethanol, and ethanol is here, negative 1367. Okay, so I have all those values in the data booklet, and I have this sort of equation. This is the equation I'm trying to solve for. I want to know what is the enthalpy change of this top one. So if we go on to the next page, question is continued. So here's the values that we looked up, and we've got really 2 choices to solve for. I can either try to relate them in an energy cycle, which is the first option, or I can try to arrange and manipulate them in the simultaneous equation method to solve for the missing enthalpy change. All right, so in this type of energy cycle, what I said before was that this value here is the formation enthalpy change, okay? The one where elements get turned into compounds. So what I have up here is the compound is ethanol. So instead of saying compound, I'm going to write ethanol. And the elements are, really the elements I care about are carbon and hydrogen. And the oxygen sort of ends up being the thing that we're going to use to convert between these guys, okay? So if I take carbon and combust it into CO2, I get the enthalpy of combustion of carbon, which is negative 394. If I combust hydrogen into water, for every mole, it gives me negative 286. Now, instead of writing out their names, let's write out their formulas. So again, here's my formation equation. This is the first time we're doing this, so I'm going pretty quickly. Try to follow along if you can. So in order to make the ethanol, 2 carbons, 3 hydrogens, and half an oxygen makes ethanol over here, which is C2H5OH. That's the change that we're solving for. But I know that I can take the 2 carbons and I can combust them into CO2. So if instead of this, if I'm doing 2 moles of carbon and 2 moles of oxygen, instead of 394, I'd have to do this one times 2 because I'm burning 2 moles of carbon. Remember, this value is the combustion value is for 1 mole. So because I have 2 carbons in my formation, I need to combust 2 carbons down here to get me 2 CO2s. Okay. And now if I fix these, I have 3 H2s. So if I'm going to turn those into waters, I'm going to end up with 3 H2Os, and I need 3 half O2s, and that would be this value times 3. right? So this is the enthalpy of combustion of hydrogen, which is written for 1 mole of hydrogen, but because in this equation, from the formation, I know I have 3 hydrogens, and it's going to make 3 waters, it's going to be 3 times that much. Okay? The last value that I have is for combusting 1 mole of ethanol, which is negative 1367, and so that requires 3 O2s, and it gives me negative 1367. Okay. So notice that in total, to get from here, I've got 2 O2s and 3 half O2s, and that's 3.5 O2s. Or if I go this way and this way, I've got a half O2 plus 3 O2s. I've got 3.5 O2s. So overall, the equations do add together. And the missing piece, or the way the math is going to work out, is that I need to solve for the missing piece that is the formation. So I've got 2 times 394 plus 3 times 286 on the one side, and that equals whatever the formation is, plus negative 1367. So these 2 enthalpy changes have to add up to the ones that are going straight from the elements to the compounds. So if I plug in the numbers and I do the math out, 2 times this one and 3 times that one, I get negative 78 and negative 788 and negative 858, and I put those together, negative 1646, and then I add 1367 to both sides to solve for the formation, and I get that the enthalpy change of formation for ethanol must be negative 789 kilojoules per mole. That's the energy cycle way to do things. Personally, I find it much more confusing, and I think it takes a lot more practice to figure out where all the pieces go. We can also solve for this thing using simultaneous equations. Okay, so the way that I've set it up is I've taken the 3 bits of information that I know the enthalpy changes for, so those are the enthalpies of combustion, and I've written them out. Then I've written the standard enthalpy of formation beneath it, because that's the one I'm trying to solve for. So I'm trying to figure out what I have to do to these equations. How can I flip them and multiply them so that they will add up to this equation? Because if I can do that, then the enthalpy changes will add up to this enthalpy change. So go through it, either starting at the top or starting with the end equation works either way. I'm going to start with the end equation and say, okay, in the end, I need to have 2 carbons on the left. So if I look up at these equations, I have carbon in this equation. It's on the left, but I only have 1 of it. So that means I need to multiply everything here in this line by 2, because I need to have 2 involved. So that makes this a 2, that makes that a 2, and that makes this times 2. Okay. I then go to my next piece. I have 3 hydrogens. The only place up here where I have hydrogen is here. I have 3 hydrogens on the left of the arrow. I've got 1 hydrogen on the left of the arrow. So that means this equation and everything in it needs to be times 3. 3. Oh, this water already got multiplied by 3 by accident prior to that, so sorry about that. Now I would be multiplying it by 3. It shouldn't have had that 3 yet. So 3 times this value. Then I get to oxygen. Now, oxygen I'm not going to deal with right now because I see that I have oxygen here, here, and here. It's in a lot of different places, which means rather than try to make it cancel out to 1/2, if I leave it alone and I deal with the last piece, I bet the oxygen will deal with itself. It's kind of like when you balance chemical equations. If you have an element that's in a lot of places, don't try to balance it, leave it till the end, and it usually works itself out. So for the last piece of the puzzle, I've got ethanol. I've got 1 of it on the right, and in this equation, I have 1 of it on the left. That means I need to flip this equation. So if I flip it, it's like reversing it. So if I flip this, I need to flip my enthalpy change, and it becomes positive 1367. Now, for the sake of things, I will rewrite this equation just so we can see what it looks like flipped. And now I'm going to go into the final cancel out mode. So because I flipped it, I'm going to cross this old one out. Okay, and so now these are the things that I need to add together and cancel out. So if we go through it, the 2 carbons is here. That comes down. It's the only place where there's carbon, so it doesn't cancel out. 3 hydrogens comes down. It's the only place where there's hydrogen, so that doesn't cancel out. And there's 1 ethanol on the right, so that comes down to here. Now, all the other pieces, let's check it out. I got 2 carbon dioxides, which will cancel these 2 carbon dioxides. I've got 3 waters on the left, which cancels these 3 waters on the right. And I have 2 O2s and 3 halves O2. There's my 3.5 O2 on the left altogether. And on the right-hand side, I have 3 O2. So 3 O2s gone, and 3 of these O2s gone, leaving me with that half O2. Notice the O2 worked itself out. I didn't try to deal with it. It just balanced itself out. So by flipping the top equation, multiplying this equation by 2 and this one by 3, I was able to add them up so that they actually added up to this final equation. So that means if I add up positive 1376, 2 times negative 394, and 3 times negative 286, I should get the final enthalpy change. Well, if you look back up at our energy cycle, that's actually the exact same math we did. We did 2 times negative 394, 3 times negative 286, and ended up adding, because we got rid of it, a positive 1367 to the other side. And so when I do it this way, I am also going to end up with a final value of negative 279 kilojoules per mole. So the math really is identical. Either way, you're still solving properly for this enthalpy change of formation. Once you get the hang of this method, it's really, I think, a lot simpler. You really don't have to go through the trouble of actually rewriting equations and canceling everything out, canceling all the little pieces out. If you can just get the key players into the right spot, like getting 2 carbons onto the left, because there's 2 carbons on the left in your final equation, I don't even bother adding the 2s. If I get my 3 hydrogens here, I just say put a 3 in front of it, and the key really is the stuff over here, the math. And what you'll see on the IB mark scheme are 2 times 394 and 3 times negative 286 and the positive 1367. And then putting those together gets you that final enthalpy change. That's how the simultaneous equations work. Okay. Here's a practice problem that we'll check out in class. And the very last piece, one more way that these enthalpies of formation get used. Just like chemical equations can be thought of as bond breaking and bond forming. And so you can use bond enthalpies. You can theoretically add up all the bonds that get broken, subtract all the bonds that get formed. That's one way to calculate a delta H. You can also use delta H of formations in a similar way. You can look at chemical reactions as though you are unforming the reactants, and then you are forming the products. And so you can solve for any reaction delta H if you have the delta H formation values for every product and every reactant. So the equation essentially works like this. You take all the product enthalpies of formation that you form, and you subtract out all the reactants that you unform. And that gives you the change in enthalpy over here. So as a specific example, I have an equation written here. Ethene plus hydrogen makes ethane. So let's see if we can write in our chemical formulas. So now that I've written in the formulas for ethene, hydrogen, and ethane, I look up their enthalpy of formation values. This is a snapshot of part of table 12, and it has ethane, negative 84, and it has ethene, positive 52. Notice it doesn't have hydrogen because enthalpies of formations of elements are 0. So to calculate the enthalpy change, you're going to do, I'm not going to bother making the delta symbol. It's the enthalpy changes of the products. In this case, that's ethane, and that's negative 84 kilojoules per mole. And that's the only product. I'll put it in parentheses just to remind us that it's by itself. And then I subtract out the enthalpy changes of formations of the reactants, which in this case is positive 52 for ethene and 0 for the hydrogen. And so in the end, the enthalpy change for this reaction is going to be negative 84 minus 52, which ends up being negative 136 kilojoules per mole. Note that if this had said 2 ethenes, I would have had to multiply 52 by 2. If it had said 2 ethanes, this would have been times 2. So anytime you multiply coefficients, you also have to multiply the enthalpy changes. So this is the kilojoules per 1 mole of ethane that gets formed. If it had been the same equation with 2, 2, and 2, it would have been times 2, times 2, times 2, and we would have had twice the enthalpy change. So maybe not the best example to show you. It's one example, and we'll practice more in class, but just a way you can another way you can use enthalpies of formations, like you would use bond enthalpies, but it's actually a lot quicker and simpler and more accurate. And you use enthalpies of formation to solve for delta H for any reaction.